Hello everyone, and welcome to another mini sky tonight. So one of the questions I sometimes get in the planetarium, it talks about why do we need different instruments on, say, for example, the Hubble Space Telescope, the James Webb Telescope, or the Chandra X-ray Telescope? Why do we need these instruments that look in wavelengths that the human eye doesn't see? I mean, shouldn't we just see the pretty pictures and everything? Well, you have to understand, different objects emit different light or different radiation, as we often call it. So sometimes that radiation tells us unique things. So by looking in different wavelengths and getting those different wavelengths and collecting data from it, we're able to understand unique things about our universe and how it works. Because our eyes, the human eyes, are only limited to the visible range. And it didn't tell us a lot. In fact, if you were to take the whole electromagnetic spectrum, it's basically the range of radiation that can emit from a body. And if you were to spread it across the entire United States, all different types of wavelengths, and just spread it across the United States, the visible range, what the human eye is able to see, is about the width of this piece of yarn. Yeah, our human eyes suck. And so since we're so limited to just a very narrow width of the entire electromagnetic spectrum, we see beautiful, unique pictures, but it doesn't tell us a lot. And sometimes we need the other ranges to tell us more about objects. So let's dive into the electromagnetic spectrum, how we use it today in our modern day usage, as well as how we use it in astronomy. So let's start with the longest wavelength, the radio light. So what do you think when you hear the term radio? Well, I know for me, I think of the radio in my car. I love turning into different music and listening to it as I'm driving into work, or if I'm driving around and going to the grocery store or things of that nature. And that is how we use radio light. And also some people would say, oh, walkie-talkies and other things of that nature. Well, what's going on is that the radio stations are sending out a electronic signal or a light wave, and your device in your car is converting that light wave into an audio signal, something that you can hear. So the tunes that you hear from your car is basically a light wave that is converted into an audio signal. And there's a whole long history of how we were able to take audio signals, convert it into a light wave, and then convert it into a radio signal. If you want to look up that history, you're more than welcome to. But how do we use it in astronomy? Well, the study of radio astronomy kind of started shortly after the World War II, when they converted radio dishes that were first looking for radio signals from airplanes and other sources, and they pointed it towards the sky looking for unique structures that also had radio signals. And they came across these unique signals that had short little beeps. They saw these little radio signals that all of a sudden had a 3-second beep, and it wasn't some type of Morse code or anything. And so they kept track of it, and they realized that this was an object from space. It wasn't until much time later that when we were able to get some other images of these different objects that we realized it was a unique type of star, a pulsar. They're hot condensed stars that rotate so fast that the jets, when they point towards the Earth, we're able to receive those signals. And they basically act like a lighthouse sort of in space, and they create these signals that we're able to detect. In fact, when they were first kind of detected, one of the astronomers called it LGM1, or Little Green Man 1, because he thought it was a signal from a life force, when in actuality it was a star. And we're also able to detect hot gases in galaxies. So we're able to figure out, like, oh, there's something unique that's going on here because it's blaring in this different type of radiation rather than just a pretty picture. So we're able to detect, like, hey, this may be a star forming region or something. So here we found some hot gases that are in a local galaxy. All right, We start from the longest and we're going to work our way towards the shortest. Next up, microwaves. Now, when you think microwaves, you think of the microwave that's in your kitchen to use to heat up your food. So how does it work? In everyday use, microwaves have this wavelength that's just a little taller than water molecules. Now, here's an example of a little water molecule with the oxygen and the 2 hydrogens attached to it. What happens in your food is that the microwaves give energy to the water molecules because they're not small enough to basically break apart the water molecule, but tall enough to transport energy into the water molecule. And when you give energy to a water molecule, it then tries to transfer that energy to other water molecules, and then all those water molecules bouncing around is what creates heat. So that's how we're able to heat up our food without any bad repercussions or anything of that nature, using something even more powerful to make it kind of nasty. So if you want something fun to do, I know when I'm getting stir crazy being stuck in quarantine sometimes, one of the fun things I used to do in college when I was a poor broke college student and I was looking for fun entertainment is what I like to call peep jousting. So if you want something fun to do, that's something fun and engaging to do with your kids as a fun treat, is you take 2 peeps or 2 marshmallows. You can even do it with marshmallows. The reason being why I did it with peeps is because I really didn't care for peeps. They kind of tasted chalky to me. So hence why I did it with peeps. So you take 2 peeps or 2 little marshmallows and you stick toothpicks onto them and you point them towards each other. And then you stick them on a plate and then you put the plate in the microwave. And you set it for about 10 to 15 seconds or a little longer, and then you watch the toothpicks as they get closer. And whoever pokes the other one out is the winner. And the great thing about it is once you're done with it, you can just take some graham crackers and enjoy the results. Another fun experiment that you can possibly do is with ivory soap. Now this is a little bit more messy, so just fair warning. Ivory soap has a unique chemical structure that when it's exposed to microwaves, it all of a sudden blows up. And this is the only soap that does it. Most other soaps, they just melt, whereas because it's air with different types of natural elements, it all of a sudden just puffs up like a marshmallow. So if you want something fun to do, there's a fun science experiment. So how do we use it in astronomy? Well, using microwave lights, we notice something really unique about our universe. It's called the cosmic microwave background. It's this radiation that exists everywhere in the universe, which is hints that a huge explosion of some kind, and this is the last residue of it, existed. So this was the evidence for the Big Bang. And we're able to see this radiation everywhere. So that's why I kind of gave us a hint that all this radiation had to come from somewhere, and this radiation possibly came from the Big Bang. Also, we use different types of microwave light to determine structures of galaxies. Since we are stuck here on Earth and we're not able to visit some of these distant objects, we kind of can't tell what they 3-dimensionally look like. But using microwave light, we're able to see kind of like a 3-dimensional structure of different galaxies. So here's a false colored image of a galaxy. It normally has these beautiful spiral arms, but we're able to see the inner structures of these spiral arms, as well as kind of how it would look almost 3-dimensionally. All right, getting into a smaller wavelength, infrared light. Now, some animals are able to see in it. It's basically heat. Our bodies naturally produce infrared light because we're naturally warm-blooded. Most warm-blooded animals create this heat that then can be seen. Sometimes we normally see infrared light when it's a really, really hot day and we look on a road and we see what is known as heat waves, or mirage waves as they're sometimes called. So we see forms of infrared light. How we use it today in everyday modern uses is sometimes we use it as our thermometers, like the thermometers that we use to go into buildings. They basically take a temperature of you. They're using some type of infrared detectors. And we also use it in medical devices to find out like where some of the hot spots are on your body. And another fun thing is that sometimes it allows you to be able to see, like night vision goggles use infrared light. which is really cool because the great thing of this is a fun image I was able to find is basically they took an infrared image of an area that was kind of desolate and they realized it was mostly composed of bats. So it's kind of crazy. Also, they use it in modern industry for like installing houses and energy uses to find out like where is your heat escaping from your house? Like where are the hot spots? Like, so where are the spots that either air conditioning or heat are escaping from your house, and they can try to seal it up faster. In astronomy, we use it to detect hot spots as well because there's a lot of gas and dust and everything in our space. So it allows us to be able to see some of these naturally emitting hot areas. Sometimes when you're looking at the weather from the weatherman, they sometimes use infrared to determine like the hot gases that are rising up into our atmosphere to give us the weather. And in astronomy, it allows us to pierce through the clouds to see some of the hot areas or like hot young stars that are being born. Because the gas and the dust are relatively cool compared to the hot stars, so we're able to see the hot stars through the gas. All right. Let's skip visible. We all see visible. We get the pretty pictures from visible. So let's now go into the next step and something that we can't see, UV light. Now, UV light is created from hot sources. So like when we go out into the sun, we have to protect ourselves from UV light, UVA and UVB, different types of light. Now in everyday use, they sometimes use ultraviolet light as in terms of creating suntans. Now, I highly don't recommend this. There's a thing called skin cancer. You guys are way too precious to be able to do this naturally to your skin. Love the skin you're in because you only got it once. So protect your skin. Use sunscreen when you're out and about. Take care of yourself. Do what you can. Like I said, I don't recommend, but that's how we use ultraviolet light in modern day purposes. We also use ultraviolet light as a means of eradicating like diseases and stuff on food. So like if you see some food that says it's been processed, chances are they've used UV light to kind of destroy any type of bacteria and stuff on it using ultraviolet light. In astronomical uses, we look at for hot gases, like really, really hot objects in space, especially like, for example, galactic centers or big, huge hot areas of star-forming regions. Next step, X-ray lights. Now, the fun history about X-rays is that it was unknown. All of a sudden, this device was creating these unknown forms of light that normally can be detected. It wasn't until it was put through photographic light or through a photograph that they were able to detect it. Like, for example, here, when we use X-rays, we see bones and everything. This is the first X-ray that was ever made, where the discoverer of X-rays took his wife's hand and he was able to see the bones in his wife's hand. So hats off to the wife that basically sacrificed herself for science. In astronomical uses, we look for really hot, energetic objects. This is sometimes how we're able to find unique types of stars in nebulas. Like, for example, this is a unique type of pulsar we're able to detect inside a huge nebula that exploded. And we're also able to detect these galactic center, like, for example, oh, apparently I thought it was a video, but apparently it's not working. So in this particular video, what the unique area is specifically right around about in here is the galactic center, the supermassive black hole that exists inside our galaxy. And it's emitting out these X-rays that we were able to detect that hint at, okay, there's something very powerful and energetic that's going on in the center of our galaxy. Next step, gamma ray light. This is the most powerful light in modern day use. Usually it was kind of first detected when we were in the nuclear age and we were doing nuclear tests and this type of radiation, how deadly it could be. So we needed to be careful with it. But with advancements and everything and understanding how it works, we're able to use gamma ray light to detect cancer. We're able to use it to fight cancer and different types of cells by using gamma radiation to take the infected cells and eradicate them. In fact, sometimes we use gamma radiation to eradicate food and preserve it. And it's not harmful to us because they do it in such a low dosage. But for gamma rays in astronomy, they are the powerhouses of our universe. They are the objects that create gamma radiation are incredibly powerful. In fact, this is a beautiful map of some of the most powerful objects in our universe. In fact, the most powerful is what is known as gamma ray bursts, where all of a sudden it releases a huge amount of energy in a matter of seconds, and then they disappear, which is really crazy that they disappear within a matter of minutes. And in fact, there is a telescope called the Swift telescope that tries to catch these gamma ray bursts on the fly to find out what they're created by. Some speculate that they're created by supermassive black holes ramming together. Some detect it as basically a hypernova, basically a really, really, really big star that goes kaboom. And there's some ideas that it's basically two stars colliding with one another. But just to give you a rough idea of how powerful a gamma ray burst is, so on the far left you see a light bulb. About 100 light bulbs is your campfire. 10,000 campfires is a nuclear power plant. Over 100 million nuclear power plants is a sun or a supernova, and then you have over 100 million supernovas to equal suns, and then over 1,000 billion supernovas equal a gamma ray burst. They are the powerhouses of our universe. And in fact, some people believe that possibly a gamma ray burst is what eradicated our planet during the time of the dinosaurs, but we don't know. But we do know that if a gamma ray burst was to go off near our planet, it could be disastrous. But fortunately, there's nothing that large or that strenuous, like two supermassive black holes colliding next to each other, next to us, that we have to worry about it. Fortunately, we are safe in our little haven of the solar system. So this is how we use the electromagnetic spectrum in astronomy to detect unique things and how it tells us some more stuff about our universe. So if you have any questions or comments, leave them down in the comment section below. If you have a topic you would love for me to cover over, leave it down in the comments as well. Also, parents, if you're looking for some fun activities for your kids to do and to keep them engaged mentally, one of the things that we do here at the Scobie Education Center is called digital badging. And we partnered with futurereadysa.org, where we create these digital badges that gives students fun activities to do, and they can get this little badge to basically honorary saying, yep, I completed it. Now here's some other fun activities. I highly recommend the Astronomy+ mission because that was the one I helped with out. And so if you want to hit some fun, engaging activities with your kids, here's some fun ideas to do it. And I'll leave it in the link description. And until next time, stay safe, stay healthy, and as always, never stop learning.